All right. Good morning, everyone. Welcome back to another session of AI-based decision support one. Yeah, now the laser pointer's working. All right. So um, I'm gonna summarize what we did last time. So as you can see here, we're gonna go into the second step of our what we call the CRISP-DM process. So this is the process on where we at the final step get to deploy an AI-based decision support system. So which is the core of the lecture. However, um, in the last lecture, we kind of explored that there are many steps necessary before that. And one of these steps was business understanding, where we had an actual business goal that we transformed basically into what we call the data mining goal, or we could call it an analytical goal. So this is the thing where we say, okay, someone says, oh, we need to get more money. And you say, okay, we need to classify the customers. For example, we need to have a classification and then we can build a model, scan for the data and so on. And also some of these important sub-steps were getting an inventory on what you actually had. And one of probably the most important inventory item or items are the databases and the data. So obviously without data, we cannot build a model. And so there are the next two steps that go kind of together, which is data understanding and data preparation. So first, we're going to get an idea of the data situation. This is very important to see what we can actually later on build, like what is possible, what isn't possible, what do we need to take care of, and we will go through through many basics. Now here's a small disclaimer. You will hear things that you probably already know, but from another perspective. So it's very important. What we always do is we kind of teach what the point of it, but also we teach it from the perspective of predictive modeling. So what does that actually mean? What can that cause? What can happen? And so on, right? And we also have some examples then that will later on be presented in data preparation. So, but yeah, let's see. So what are the learning goals for today's lecture? Or maybe we will step into next week a little bit. So the learning goals is actually we want to see what does data comprise, like the term data. What is data? What kind of data can we use? Is it just like a table data? We know that there is a lot of data types. We can use image data, audio, video, text data, use any kind of data, but we will talk a little bit about what are the difficulties in with the different data types. Um, and then how can we look at data before the modeling phase? So obviously we need to, before we build a model, we need to look what do we have? How does it like compare? What can we do with it? And sometimes also this is one of the important focus here because we're not like in statistics where we want to see which factor influences what other factor. We will touch on this a little bit because it could be important for some more shallow machine learning modeling. However, uh, our our main theme here is to give an input to data preparation, right? So that we know what kind of data problems there are. And yeah, and we will use descriptive analytics. So you remember the different types of analytics. So this is where we actually use descriptive analytics to get an idea. And you have an optional learning goal. So you will see at the end of the slides, if you look through the slides, there is a really large Python example. But as I said, this is an optional learning goal. So that I will not ask you about the Python example in the exam, obviously. But if you want to learn more, if you want to implement it, the data set is either you can download it from Kaggle or I think it's also uploaded in the e-learning. So you can, if you want, besides the data camp thing, which is mandatory, you can also like test your skills and everything is explained. We have a lot of slides. I will go through it maybe a little bit at the end, but so this is a cool opportunity for you to see how data is prepared, how to get some meaning in a prediction task, and so on. So this is a pretty cool hands-on addition to these learning goals, right? But obviously, this is more like for you to cover by yourself and everything is commented. Okay, so you know this. So as I said, for business understanding, we move to data understanding now. So, um, and again, we will go through the different steps here fairly quickly, right? So, what data understanding is, I guess it's pretty obvious. What we need to do, the first thing is like collect initial data. So why initial data? Because usually a data collection will change. So as I said, sometimes this is iterative, right? So everything can be iterative, but especially from data understanding to evaluation, like this loop. So we evaluate the model, right? And then we see, okay, for example, we need more data. That data is not cutting it. We need external data, for example, we need tweets, we need other text data, we need to look through our emails, we need other internal data, like we need other data needs to be provided, or maybe in the future we need to collect this data. So this is why it's called initial data. So this is everything we have, and we try to do our best with that, what we have. And then what we do is we're going to look through the data, we describe the data. So this is descriptive analytics. We have an idea, but the important thing is that the data description, it should be guided. So it should not be like, oh, we're gonna have like a report like this report here. It should be connected to your business understanding. And this is the most important thing. This is why we have that here. So we don't suddenly forget that we have that we did all the business understanding. Remember, with all the constraints that we have. For example, we had this manufacturing example with speed. So what we would be interested in the manufacturing example, while we want to detect errors, is actually what kind of data do we need? So we need data of the product that is being manufactured. So what are properties of the product? What are properties of each of the stations, like maybe sensor readings, temperature, and so on. Maybe we have a camera, so we need an image. We need image data too. And so this would be an initial collection report, like what do we need, what do we have, right? So for example, if we don't have a camera, we could like later on say, okay, that you see here below here, there's a data quality thing. We need more data, or the data that we have is not good. So describe the data should be guided by business understanding. So we do not describe every piece of data that is in the company, right? So it has to be with regard to the goal that we set here. So for example, we would probably not be interested in like data of employees, HR data, maybe bookkeeping data. We also don't need because it's about manufacturing, right? So we won't use every piece of data. So this is guided. This is probably the most important thing to tell you here. Yeah, so described data is just like a description where we say, okay, this is like the mean, for example, and explore data is something where we go a little bit more into detail, like correlation analysis. But as I said, this exploration, this can be part to see, okay, what data goes together. Are there some preliminary effects maybe? So this is especially, as I said, this is specifically important when I use shallow machine learning, because we know from the difference. So if we look forward to the modeling phase, as I taught you in the beginning, with my example with the child and the sports car, there are two types, right? We have the shallow machine learning, where the mother actually tells the child what to pay attention to, right? And the other thing is deep learning, where we actually where we just say, hey, look at the car, right? So and now the data exploration helps us identify basically some basic features that we could tell the child, right? In the analogy, right? So that means in shallow machine learning, we put the variables in ourselves, right? And so the explore data can help with that. Okay. So this is the importance between. So explore data is we look at how different variables, what's their relationship basically. And here in description, we just look at things like, okay, we look at how can we describe the data, how can we maybe some means and so on. So, but they obviously go together. So they just have like small differences. Okay. But you see here always it's about the data mining question. Yeah, then we have the data quality, which I said. So we also use this. So we also use these tools. So basically these two tools, the description and the exploration, we can summarize this as one step if you want. Like you don't necessarily have to distinguish them. Like it might be okay that we say, okay, this is more like constructing the table, right? Having the format of the data, the quantity of data. So this is more like meta information usually. So this is like not means. This is like, for example, what kind of columns do I have? Like a database model. This is fairly important because we might want to know the data types of the column, how they are saved, and what kind of are they, like, for example, an integer value? Are they a real value? Are they a character value? So that we know that, okay, we know that this variable might be a nominal variable. So, and it's saved as an integer, which doesn't make maybe sense. So the software can mistake it for another thing, but we will talk about this in a few minutes. So don't worry about it. So this is more like metadata, like the columns of the table, and the data types, like how many rows do I have, how many columns do I have, what data types are the columns. So this is more like about the data table, and this is more like about exploring the data, how do different variables go together, and what's their relationship, and also how single variables, maybe some mean values, some distribution of single variables. So the thing when we look at single variables, we call univariate, and if we look at two variables, how they go together or how their relationship is, this is called bivariate. But we will go through this, and at the end we will use the exploration. So as you can see, this is the input for this step to verify data quality. So this is rather important for us, because in data preparation we need an idea on what do we need to deal with. And this is also kind of depending on the modeling. So there are some methods that require some sort of data. So if you use some kind of easy tools, like for example, I'm gonna put it in the chat because it's quite cool. You should check it out. It's called RapidMiner. Is it called RapidMiner anymore? I think it's called RapidMiner. If you Google RapidMiner, download the version. I think you can even get like an academic license, which is pretty easy. So download it, apply for an academic, and play around with it. Do the tutorial. It's really cool. So it's a graphical tool. It's not like Python. I know Python is the way to go. This is why we learn it. But sometimes I use this tool just to play around a little and have easy modelings. And you should do too. You will see it's a cool tool for rather simple tasks, and you can build quite elaborate models. And you have, if you get to know the tool, you can build quite elaborate also analytical processes that are exactly what we have here. Like you can even deploy it on the web. So it covers all these steps, right? So that's pretty cool actually. And and the problem is, what you will see when you use the tool is, if you have like some modeling techniques, that there will be an error where they say, okay, this is not the data type I expect, or we cannot handle this data type, and then or we have too many missing values or something. So this is where the data quality, we have to look at missing values, we have to look at different data types, also other things. So the technical things where it won't work technically, right? But so this is one thing. So this is where you get an error from the tool, but also other things that where the tool says, okay, fine, we can actually do this, but it's not good, like imbalanced data, outliers, and so on. So these are the things we will talk mostly about. Okay. And I've selected, of course, some of these problems, and we will talk in data preparation. We will talk about how we can solve this. Okay. So this will be the part of data preparation we will do in the next or lecture after this. Okay. So as I said, all right. So and I'm saying details. All right. Collect initial data. So I will skip these steps because I just explained them to you. So there is no need to do it again. So just what I want to do is maybe just go over some of this here. So the verify data quality, as I said, missing data, data errors, measurement errors, and so on. But we will talk about this in detail later on. So, okay. So what is data? So there's a weird dictionary, explanation, and also here we see the data trends. Obviously, it's like the word data was not really popular back in the 1880s, but yeah. So just some ideas. Okay. Generally, when I skip slides, right, I either explain them beforehand or they are not that important. You should know that, right? So they are there if you want to read it again and if you want to go into details. So it's fine. But the important thing now is what kind of types of data are there? Because this is what we need to face. And as I said, in the manufacturing example, I overloaded you with like 3 types of data. So we have data in form of tables, where we have, for example, what kind of product is it? What's the name of the product, the size of the product, maybe, sorry, half-life of the product, whatever, right? So, and then there is data that comes with time, so that we have time series data like sensor readings every 15 seconds, whereas the data of the product doesn't change frequently. So of course, if they change it, so if you're manufacturing a car, so you're manufacturing a BMW X5, so you will see, okay, then there is a new X5, then the data will change, right? But until then, this will be constant. So it won't change for every car they produce. It will stay constant. However, the sensor readings will be different every 15 seconds, right? So this is, but you have to integrate in these kinds of data. So as I said, what we have, we start with fully structured data. So basically what this is this is your classical table, right? You have the table format where you have your variables and you have your rows, so your columns and your rows. Then we have unstructured data. So which means that it cannot be put in in a table structure. So we have no object with properties, but rather it's unstructured. So examples here are usually images, video, text, right? So this is data. But as we know, we use this data frequently nowadays. So there is of course a way on making this data readable by the machine learning model, right? And we will talk about this, specifically images and text, in AI BDS2. I will give you a small heads up how it's done so that you don't have to wait this whole semester. But um, so basically for images, what we have is when the computer reads an image, we basically have a matrix, right, of numbers of RGB values per pixel, right? So it depends on the size of the image. So let's say we have 100 by 100 pixel. And what we have then is we have, just see, so image. In an image, so let's say we have an image. So this is, let's say 200 by hundreds because I draw it not quadratically image. And then we have like pixels. So we have 200 pixels here, each in each row. And so basically we have some sort of column and row thing, but it's not really structured because this is not an object. This is just a part of the image, right? So we have a pixel here, and each pixel here has a value of 0 between 0 and 255, right? And now this would be for a grayscaled image, but we know that there are images that are not grayscale, like, so we have an RGB. So we have this 3 times. So we have this for R, for G, and for B. So basically we have multiple of these matrices, right? So we have this for, this is R, this is G, and this is B, right? So, and we have these numbers here, and this is our input for one image, right? So basically, if we translate this into a data table, right? Basically, if we would translate this into a data table, which is possible, we have here, this is an ID column where we have and we have the first image, right? And so what we would have is, if we were to put it into a traditional data format, we could do this because this has properties, right? And the properties are the pixel values. So we would have R, would have the first, like the first pixel, R1. Then we would have another column that is G1. Then we have another column that would be B1, and then we would have R2, right? So this would be the second pixel, this one right here. So for each of these pixels with a free, and you can imagine there's a lot of columns, so we need to kind of do it in another way. But actually, this is how we read it, right? This is how we do it with images. So but you can imagine there are some techniques in the model. There need to be some techniques going on in the modeling to deal with this large amount of data that we have, because this is only one image. But we know to train a model, or we don't know yet, but we will know that we need a couple of more images probably to do that, right? So need maybe, yeah, some images, K images, a lot. So, and for each of these images, we would have a large number of pixels. And so we need some way of the training algorithm to deal with it. And obviously we cannot do it by hand. So this is where deep learning then comes in. But this was an optional like preview. Like if you ask yourself, how can we read images? What's the deal? Just to serve your curiosity. Okay. So fully structured data, unstructured data, there's semi-structured data, which is a little bit in between. So where we have some kind of structure, so things like XML, RDF. So when you have like, for example, certain tags, like we use to data mine job descriptions from Indeed, and it will help. For example, you have like this thing like description, and then you have like a text, right? Blah, 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 blah. And then you have like an end description, right? Is it this one? What is it? This one probably. You have like an end, and so this will be structured because we know this is like the name of the table. So again, if we have this in a table format, we would know the column name. Actually, here we don't even know the column name, so we had to take care of this step by ourselves. And here we could have descriptions. This is the job ad. So this is the first job ad, and the job description is then just like a text here, right? And here we have another text. And of course, if we want to do something with the text, we would need again some kind of transformation, but we will talk about this later. Okay, so text we need to do differently. We need to deal a little bit differently. But yeah, I see you're curious. Without asking, we're gonna do it. So let's say this is the first description, right? So this is the ID first description. So instead of just having it in one column, what you do is you have all the words. So we could, for example, word one, word two, all the words of all the texts in the table, you have them right here, right? And then you just count if you have several options. You can count binary. Is the word in there? Yes, no, no. You can count how many times it's in there, right? So if the word is 2 times in there, you can just like 2. And then there are some other options where it weighs the frequency of the word against the frequency where how frequent the word is in the whole body of documents, which is called a corpus, right? So yeah. So this is how we deal with, how we used to deal with text. So this is how we used to deal. It's called bag of words, and it's old, and we don't do it. We don't do it anymore usually. But what we do is we use embeddings. But this will go too far now. So I will stop. I will just throw you the words. So from bag of words, we went to embeddings. Because you can imagine the problem here is that I have a lot of zeros because I have all the words from all the texts, and so I have a lot of columns again because I have a lot of words usually, and then I have a lot of zeros and some ones. So this is a sparse matrix, right? This is a matrix that has very many. So this is also brings problem of its own. So we want to have a different approach on how we can characterize these documents, how we can characterize one document as an input for the modeling. So it's all about how can I characterize. If the data is not structured, the question is always how can I put the data in a kind of structured form or in some kind of form that I can use in the model, right? So this is the idea for unstructured and semi-structured data. Fully structured data is usually in a table. So let's have a look at fully structured because we will obviously start with that. As I said, text and image will be in AI BDS2. So don't worry about it. We will stick with classical structured data matrix here. So, and now you might think, oh my God, he thinks we're stupid. He's explaining a data matrix. Yes, I am, because it's very important. And also I want to give you some practical advice, right? I always shout it out when I say, hey, this is some practical advice. So this is probably the most important takeaway from that slide. So first of all, why do I show you this? Because you have to understand what a data table is, what it always is. It always has an object, right? The object is always the row, right? So the object is always the row. And one object, right, here is, in my example, this is a person, right? So this is the first question you always have to answer. This is a practical and very important advice for you. You always have to know, what does one row in my data table represent? What is it? What is the object? What is the object in my data table row? In my data table row. So you have this object, person one, right? And then you have attributes. We call them variables. In machine learning. We call them features, right? So these are features, as you say, these are features, these are the columns. And these are properties of the object. And all of the objects have this property, right? The property can be different, right? But it's the same property, but the characteristic of the characteristic is the same, but the expression of the characteristic can be different. So for example, age, so this person is 23-year-old. This person also has the property age, of course, right? But has a different value for it. So this is how it's done, right? So these things needs to be common for all the objects. And you have weight and height and so on. Okay, so and why did I stress it out that I want you to know what one row of data represents? So this is a fairly easy example, right? But there are some caveats here, some problems that can occur. The first problem we have right here is the granularity. So on what level is one row? For example, here, what is one row here? So it's the exact same variables, but what does one row in this data represent? right? This is what I want to know. What does one row, what is the object here? You really need to, this is analytical thinking. You need to see this because it's not you who generates the data, especially not in machine learning. So what does one line of data represent here? This is the most important question you always have to ask yourself. So be my guest, put it in the chat. We want to discuss this a little because this is a very important point. Yeah, so the object is not the country ever. The object, a row, is data about a country, but strange data. Yeah, so, okay, it's strange data. So what I want to show is that one row is a country, right? Represents a country. And yeah, you correctly said, so these values are average values. So first of all, in the data table, I needed to call this like average age, average weight, average height. So first of all, the data table is not well formulated. So the description of the data, remember the description, the metadata. But here we have, I wanted to use the same variables, but here one line, one row represents the object of a country, right? So it's a whole nother granularity. Yeah, and of course it's a little bit strange to have like the average age, the average weight, the average height. Might weight and height might not be strange, the age maybe a little bit. But I wanted to show you that you really need to have a look at what really one line of data is. You cannot always see from the variables, right? But you need some additional information usually. So for example, what if we have sensor readings, right? So how often do they occur? This is important. Which object are they attributed to? Is it like, for example, each of these rows could also be a machine at a certain time. So when you have time, you will have, for example, machine one at 12 o'clock, machine one at 12 o'clock and 50 seconds. And then you have all these sensor readings for the machine. This would usually be the data set when you had sensor readings, like in our example where we manufacture the solar panels, right? And we have the different stations, and for each station we have the data. And then we had all these, we had this large database where we can actually see what's going on right now, right? So this could be a large data table where we have all these different things. Like for example, we would have a large table, right? So just give you an example. So we would have time is t. So we start at 0 maybe. And so these are minutes. Like we could also have like, these are like something like this. And then we have minutes. So this is, if we have every 15 seconds, we have a reading, for example, right? And 30 and so on. And then we have, for example, station one, temperature sensor one, station one, temperature sensor two. And then we have a lot of more. Then we have station one, vibration sensor one, right? And then we have, of course, again, then we have station two, temperature sensor one, right? You get the idea, right? So just to show you some other data and again, now what here you have to know what one line of data represents, right? So it's a certain station. So it's the machine, it's the machines. So this basically one line of data here represents a snapshot of manufacturing, of the manufacturing plant, right? Or manufacturing street or whatever you want to call it, like the conveyor belt or manufacturing machines, right? Snapshot of manufacturing machines or manufacturing stations, right? At T. So this is important. This is one row. Like what does one row of data represent? And it equals is a snapshot of manufacturing at T, right? At this exact time. So this is a rather important variable. So if we have time, then the data changes slightly because we have like the same reading but 15 seconds apart. Okay, so just so you know, because time is usually an important variable here, an important indicator. We usually in manufacturing, if you have a process, of course, time plays an important part here. Okay. All right. So continuing and having said that, So the features, now we're talking about the features. Remember, the features are the variables here. So now it's important to know that there are different kinds of features. So, and with different kinds, I mean there are different kinds of information value that it can hold. Like what kind of information is encoded, can be encoded in the feature. So we're going to start on the left-hand side. So the features are usually measured on scale. So with measuring, I don't mean that I as a human need to measure it. It comes from that probably, but so you can imagine how they are expressed, how I have them in the database. And that doesn't mean that actually this is the correct way, but usually in machine learning or in an organizational context, you encounter data and it's just the way it is. So maybe you have to transform them, right? You can also transform them. But the true scale needs to be known, but usually from the variable, it makes sense that, okay, if this is a temperature sensor reading, you will know, okay, this is a ratio scale or an interval scale, right? So we start at the left, nominal scale. I'm gonna just say to you what it does and what it cannot do. So nominal scale, the only thing I can do with the nominal scale, I can say it is or it isn't. Remember that. It is or it isn't. So it is green, it is red, right? And so on. So this is a nominal scale. Nominal scale usually combined with a domain that is discrete. So usually I have a limited amount of options here, what value my variable can take here, right? So there's a limited amount usually. So examples are gender, colors, and so on, right? So now, ordinal scale, I can say it is or it isn't. So this is always the case, right? If the scales grow basically in information value. So, but I can do more with it. So with nominal scale, I can, for example, count. I can say, okay, there are, if I look at the cars, I say, okay, there are 5 black cars, 4, because I can say this is a black car, this is a black car, this is a green car, and then I can count, right? So this is the only thing I can basically do. I can build no average or anything else because, yeah, I cannot build an average of colors because I can't just say it is or it isn't, right? So what I can do with nominal, I can say what is the most frequent value called the mode, but we will get to this. Ordinal scale, it is or it isn't. So, but also what I can do, I can say some value is larger than the other, right? I cannot say by how much, but I can say it's larger. For example, place in a race, right? So I can say, hey, you won first place in this race and you won second. So I know that the first place is better than the second place. I can order them. This is why it's called ordinal. So here I can say it is or it isn't, and I can order them, right? So another example is the example you all know when you filled out a lot of soft surveys. So I totally disagree, and it goes to I totally agree, right? So it's like negative, and then it goes like into I totally agree. But I cannot tell you the difference, right, between the options. I just know that the one thing is better than the other, but I don't know by how much. And this is where we come to interval scale. So in interval scale, I can interpret the intervals. So I can say by how much. For example, remember when I said, okay, you are first, and you are second. So this would be ordinal. But now if I add the time, so how much seconds did it take me to finish the race? So it took me maybe 23 seconds to run the course, and someone else took like 21 seconds. So the person with 21 would be better than me, but I can also say by 2 seconds. So I can interpret the interval between 23 and 21 seconds. It would be 2 seconds. So I can actually calculate the interval. Here we can do a lot of things. So these are like numerical scales. So we can say, okay, we can interpret the difference. We can have an average. Like if I have the time, I can build an average. And with ordinal scale, I cannot do an average, right? The only thing I can do with ordinal scale is I can say I can do kind of an average, but I cannot do like an algorithmic mean. But what I can do is like I can build the median, so the value that is in the middle. So because I can order them, right? I can order all my values, right? And then I can say the one in the middle, this is like some kind of mean value, right? But it's called the median then, right? Okay. Interval scale. as I said. And ratio scale is if I have, similar to the interval scale, but in addition to the interval scale, it occurs when I have a natural 0 point. So when 0 really means 0. Like for example, in temperature Celsius, we don't have that, right? Because we have a 0, but it goes on to the negative. So, but in weight, it will be. So for example, in weight or height, like you see here, it means that 0 weight is 0 weight, right? And 0 height is 0 height. Why is this important? Because then I can build a ratio, not only the interval, like 23 seconds minus 21 seconds is 2 seconds. This is the interval. But I can also say, if I took 20 seconds and someone else took 10 seconds, then what I can say, okay, he was faster than me by the factor of 2, or I was 2 times slower, right? So I took double the time, I could say. So I couldn't do this if we, for example, 20 degrees Celsius is not half of 40 degrees. It doesn't feel like half, right? You cannot, like this, you cannot build the ratio. You can technically calculate it, but it's not really there because there needs to be a 0 point to do that. Okay, so but usually you can summarize them, so it's not like we will largely differentiate between the two. This is more like a statistics thing. So we have nominal, ordinal, and numerical scale. Like, okay, all right. So then we have the domain. I said discrete. So usually in nominal, ordinal, you have like discrete, and then continuous. Just an important thing in the domain is that this is the potential domain, right? So because when you have a data set, the data set is always limited. That this does not mean you have infinite values. Yeah, this is just stupid. It's about the potential where the potential values this variable can take on. Of course, we have limited number of persons, right? But potentially this could be a value that is not, this is not a discrete value. We cannot only choose out of like 4 heights. Like this could be an infinite amount of heights theoretically, right? So this is what it means. So this would be continuous. And discrete is like, for example, okay, I only have 3 options, for example. Yeah, I have a car colors. I only have black, red, and yellow, right? Okay, so this would be discrete. You can also transform continuous into discretes, no problem, right? So this doesn't mean like everything has to be set beforehand. You can like transform whatever you like. We will also talk about how we can do this. But yeah, so this is kind of semi-important, but yeah. So this is important because for continuous variables, we usually, if the continuous variables are our target variable that we want to predict, we usually have a regression problem. And if it's discrete, we usually have a classification problem, right? So this is why this is important, right? So if this is our, so if dependent variable or if target, we're going to call it target variable. So the target is the thing we want to predict. If target is discrete, then we have a classification problem. So this is important for business understanding. We know that from business understanding. And if the target is continuous, we have a regression problem, right? This has nothing to do with, like linear regression and stuff like this. These are problems. These are not models. It's very important. It's called linear regression, but it has nothing to do with the regression problem. It actually has, because it's also a regression problem. However, there are also other forms of regression that actually solve classification problems. And we will deal with that. So regression, also business understanding, we need to define it. Okay, so this is why this is important. As I said, I try to make the connection for you. But this is for target variables, right? Very important. The target variables is basically the Y variable, right? That you try to, and X are the features. So, all right. Okay, so now I said already, so there are different ways on looking at data, and I think we had all kinds now. So cross-sectional data means in a data table, I have snapshot at one point in time. So for example, this is an example of cross-sectional. I have persons and they are measured at one point in time. Like for example, this person in 2 weeks could have lost weight, could have gained weight, right? Weight is here. Probably not gained height, but yeah. So this is like a snapshot, right? This is what we call cross-sectional. So it's a cross-section at one point in time. Now, time series means we have data that goes over time of one object. So for example, this could be This could be stock prices, and panel data is like a combination usually, but this is more like this is a statistical thing. But usually in machine learning, we usually have some sort of this, but panel data is more statistical. But yeah, so for example, this one, the example that I had here, so we have time, and we have multiple stations over time, right? So for example, if I had the graph, like we could have station 1, station 2. This is the temperature and this is the time. So we have different temperature readings here, right? So could look like this. Okay, so that you know this is like something like this. Okay. So, but usually we say, okay, time series data is where some sort of dynamic, the time. So we have many readings over time. So usually time series data, and usually we always have more than one object that we look at a time series. But if we only want to predict like one stock price, then it would be classical time series data. This is also called that sometimes multivariate time series or something like this, right? So, okay. So now what we did was we actually achieved our first learning goal. So we had an idea of what kind of data is there? Why is it important to know something about this? So let me give you an idea what are really important things here. The important thing was from what is data is that you have to know what one line of data represents. This is like the best practical advice I can give you. And you can see here, for example, the granularity, have to define it. And here it's really important to know which kind of data. So this is maybe one thing, how the data is scaled, because we can do different things with it. And this will be important now that we dive into the data exploration, because we cannot calculate everything for every kind of data. This is why we did this beforehand. Like I said, we cannot do like an average of nominal data. Like we have some sort of average measure, but we actually have, it's not really an average. Okay, so the important thing here is like I need to say this. So remember, I put it on slide. Usually we have large amounts of data, like well, certainly larger than any than 50 more than 50 rows. Okay. So it's pretty important that we get an idea here, but I will use in my examples, they will be small so they fit on the slide, right? So the examples, they do not feel really machine learning like. Okay, so I'm sorry for that. We will look at large examples. We will have a lot of this, but obviously I cannot put like a table with 100,000 rows or columns on the slide. So also it wouldn't help you to know this, but you can imagine from the examples that I give, like this example here, that this will go on and on and on here, right? Okay. All right. So before we start data exploration, I will give you an idea. So I will structure it because structure always important. So so usually we have statistics, which means these are numbers, right? So these are numbers that we use to describe. And yeah, graphics are graphics. I don't have to explain it. So graphics are just graphics like histogram, box plot. You know a lot of them probably from statistics, but I will show you some of them. And so then what can we look at? I already said if we look at one variable, so data of one variable, if we look at one variable, so this is one variable, one or one feature. This is one feature. And these are two features that we look at. And we have different ideas on what we actually want to do with this, right? So with one variable, we want to look at where the variable is located, what's the deal with it. So for example, if I have a temperature reading of a station, as you saw in my example, every 15 seconds I have a temperature reading. And I want to know like for each hour, sorry, the average temperature so I can see if something is wrong. So I will use univariate analysis, right? I will calculate the mean, and then I also want to see how the data changes, how frequently the data changes. Then I can use something like variance or standard deviation. Now, if I want to see how the temperature goes together with the the vibration or the product quality or something, right? At the end, I will use bivariate. I will use correlation. I will use the temperature and I will correlate it with the quality at the end, right? I might need to use an average value because it's different, what we call different resolutions. Like I can read the temperature every 15 seconds, And at the end, for each manufacturing process, I only have one, it's okay or it's not okay, right? But I measured like 100,000 temperatures probably during this manufacturing process, right? So I have to find a way on correlating this. So I have to calculate some average beforehand. So sometimes I need to do univariate, univariate. And this is again an optional thing, right? For you an optional thing, but very important. You need to oftentimes you need to deal with what we call variables that have different resolutions, like in the production process, right? So I'm gonna go back a little bit. So here, right? So we have the machines, but what I can add here, what I could basically add here is just get rid of this so I can add something here. What I could add here basically is I could say, okay, um, production, what kind of production process is it? So this is the first production process of the day, right? And then it could be the second production process. And until the second production process, and for this production process here, at the end, right, I have all these values every 15 seconds. So I have a lot of values. Like, let's say it takes like 3 hours for this to run. Okay. So you can imagine how many values do I get, right? And now at the end, right, at the end of the production process, like at the last timestamp, I have like, for example, success, right? I have success. So I have here no values, of course, because I can only, and the last value would be yes or no. So was it a success to manufacturing or did it have some errors or maybe number of errors? I could also, I could also have, for example, number of errors after each station. So I can, after this station is done, after this station is done, because this station will be idle, like the station two, the station 2 will have a temperature here, right? Obviously, but it will be idle for the first part of the production process, right? So the temperature probably will look like this. So high temperature here, then it will go to station 2 at some point, then it will go to station 3 at some point. Sorry, station 3, I don't have it here. And then at the end, so you see the different resolutions. So there are many options and you have to be creative on how you combine these into one data table so you can build a model, right? So this is probably an optional practical advice on how you can think about this, right? And this arose from the question how we can look at the temperature and this one value that we have, right? So we need to like summarize the temperature in some sorts. Okay. All right. Okay, so let's go on. Like univariate statistics, so we start with this. You can see it on the top right here where we are at the moment to give you to have an idea for you where we are. So we start with univariate, obviously, and we start with statistics. So statistics, univariate, right? So this you know from statistic, right? And then what I want to do is I want to play some sort of a little game where we see, okay, why is it important? So I drew this thing. So univariate means you have this thing, like you have one variable. You don't have two variables, so you have this scale basically where you say, okay, blue is all the data points, right? So I put in all the data points that we have here. And then we have all these other values, like we have the mean, for example, like it's 24.16. So this is one statistic. Don't worry, I will go through them. And then we have the standard deviation that gives an idea on how the data spreads around the mean. I will talk about this in a second, right? The important thing is that you imagine it as what we want to know is there are two kinds of measures. So there are the measures of central tendency. So we want to know where on the scale does it lie, right? So in terms of age, we're interested, is it like, do I have like more older people, younger people? And I want to know it at one glance. And this is the gist and the important thing of a statistic, right? It's called univariate. We know that we look at one variable, and statistic means we compress the data into numbers, into one number usually, right? So we have all our large data table and we compress it into one number, right? So this is the important of statistics. Like statistics, you can also say, okay, statistics does mean, okay, I have a number that summarizes my data set. That's it, right? This is a statistic. And so central tendency statistics say, okay, where does it lie on a certain scale, right? And variability means, okay, how does it spread around that scale? And both information together give you like some sort of what we call distribution information. It's pretty cool. Yeah, let's go through first the measures of central tendency and then the measures of variability. Okay, measures of central tendency, I always have this easy example. So let's start with the example before I actually explain it. So ER arrivals, so emergency room arrivals in 1 hour. And these are different hours here. And so we want the average. Now we want to calculate the average number. So you all know the formula of the average, right? So it's as simple as that. So usually I explain formulas. Here what we have is we just add all the values up and then we divide it by the number of values that I have. So it's, yeah, this plus this plus this plus this divided by 5. So there is nothing tricky here in the formula. However, and now we come to the part where we think about what's critical here, right? So what does this mean? What does this mean? You might think, okay, I've done this. This is a pretty easy formula. Why is he talking about a mean? I'm going to leave. This is boring as hell. Please be aware. What happens if I have like a Grey's Anatomy style event here? You know, I'm not sure if you watch Grey's Anatomy. I was forced to once, and I felt like we watched like 4 seasons of it, and in every last kind of the last kind of 2 episodes, there was some kind of disaster, like a ship disaster, a tunnel broke down, or whatever, a plane crashed, and so this was horrible, of course, but it led to the thing that the emergency room was always extremely crowded, right? So what if in this case something like this would happen, right? So I want you to, you don't have to calculate it like, but just tell me. First of all, think about what is the point of a univariate statistic. I just told you, right? And now what happens if we skews the data? So this skews the data. This is a philosophical question, right? It skews, yeah. So it skews the data if you think about it. If this was before, and if we add this, it skews the data. However, the data is what it is. So we can say the data is skewed. So skewed means it is not like symmetrical anymore, right? So it's not like symmetrical anymore, right? So we have a mean. This is 3.6. This was the old mean. And so we have something to the left, something to the right, right? So we have 1 here, there's 1 point, and then it's somehow symmetric. So skewed means it looks something like this, right? So this is like a skewed distribution, or also if we have it like, because this is like a probability distribution, if we have it in the box, but this would be a skewed. Like we have some here, and then we have this outlier here. Also, if we had this here and say, okay, we have this box plot, then the outlier would be here. And so you're totally right. It would skew the data if this was beforehand. Okay, let's see other answers. It would be an outlier. It would be an outlier. We need to talk about outliers. Okay, first I'm going to record our average data is no longer representative. That's a good point. Average should cause bias to the data. Bias to the data. Okay, we have to talk about some things here. So I will use all the comments you made because this is a very fundamental idea. There are some very fundamental and good ideas here. So first of all, let's talk. What do we have? It skews the average. It skews the average. Yeah, it skews the average. That's right. So at some point you say, okay, it skews the average. However, I want to ask you a philosophical question, right? So everybody thinks that some sort of bias, it skews the data, it taints the data, and good point was also it's no longer representative. Like Ahmed said, it was no longer representative. Marlon said it skews the data. Shami says it was being outlier. Average no longer representative. Exactly. So you basically agree with Ahmed. Cause bias to the data. Okay. So I'm gonna ask you philosophical question. Now this all sounds very negative, right? So it sounds very negative. So I want you to put it into relation and practice analytical thinking. Now you say it's biased, it's no longer representative. However, it's the data. It's what we have. It really happened. So this is nothing I came up with, right? So yeah, I came up with it, but this is nothing that is like, this is not a mistake, right? This is not a mistake. So I'm gonna write it here, not a mistake, because it could be a mistake. So start with the easy idea. We start with the easy idea that this is a mistake, that someone, like, it was actually 3 and it was actually 3 and 8 and someone put in 38. So there was a problem, like a measurement error or whatever, could be, right? So if this was a mistake, then certainly it would be easy. Then everything you said would be totally true. It would skew the data. It would make it unusable. The mean would no longer represent the data. Okay, now let's assume it's not a mistake. Let's assume this happens, right? And what's the task of the mean? The task of the mean is to represent the average ER arrivals in 1 hour, right? So it is part of the data. So it represents the average in 1 hour. The problem is, and then we come to the concept that was named an outlier. So an outlier can be two things. An outlier can be a mistake. So it just occurs because it's a data problem. We call this a data problem, a data error, low data quality. So we have an outlier that is made by mistake. So this would mean we could remove this and we could return to our old mean. Fine. Okay, this would probably be it. Now it could also be I like to use the word an anomaly for that. So an outlier has to be discussed, but an anomaly is something that is interesting, right? It's also a more interesting word. This is why I use it. But this is only something I do, right? So it's not like a law that you have to obey to, but an anomaly. So let's say this is anomaly. So what do we do with this anomaly? Like, what are my options here if this is not a mistake? Like, what I could do is I could say, okay, I could do the same as with the outlier. So I could say, hey, okay, I'm gonna remove this because it was an outlier. So I go back to 3.6. But I know it was an anomaly, and what I depends on the purpose that I connect with the statistic. Do I really want average, normal, and we think of normal? Do we really want a normal day represented? This is the question. Like, let's say these are 24 hours or these are 5 hours of the morning. Let's say this is a morning, right? This is a morning, because there needs to be more information. What is my mean for, right? So I want to represent the morning 5 hours or the morning 6 hours, and now this comes up, right? So what if my purpose is to represent to report this number and say, okay, I want to build a model that covers the average, that predicts the average number, right? Then I might use only this, right? Because otherwise, what would happen is, now if I add this, of course, my average would go way up, right? It would go way up. It is an anomaly, and it even doesn't fit, right? It simply wouldn't fit. Like, but if my idea is to also incorporate these anomalies, what would I do? Right? So what would be a better idea? Because you are somewhat correct. If I use the average and we know that the mean is somewhat very seriously affected by unusual values called outliers, right? As we saw here. So it doesn't serve the purpose anymore. However, if we want to predict it, like, this could be of interest. How do we keep this idea alive? So what we could use median instead of mean. Yeah, this is the technical solution. But okay, so this is the solution if we are interested in what I just said. Just a representative morning, we could use the median. This is technically correct. However, then we would lose this. Like, just assume I give you a report card, and I'm gonna let's calculate the median here, shall we? Let's calculate the median, okay? So median is, so first of all, median comes here, but we're gonna calculate it just to I want to do this idea. So we order it, right? So the first thing for median, you order it, you bring it in the right order. So we have one, start with the smallest, 1, 2, 3, 4, then comes the 8, and then we have 38, right? All right. So, and then you have 1, 2, 3, 4, 5, 6. Okay. Then you take usually 1, 2, 3, 4. You take the middle two numbers here, and you can like either, so there are different approaches. You can either pick one of them, like the 3 or the 4, or sometimes you can do like 3.5, which is weird if your data is not numerically scaled. So if it's ordinal data, you have to pick one, basically. And so let's say, but for this we can do it because it's numerical data, like this is interval scale, this is even ratio scaled. So we have 3.5. So this would be the median would be 3.5 median. So cool. So this means if I report you back this, you will never, and if you don't look at the data, please assume that summarized statistics are there so people don't look at the data. So I give you 3.5. The anomaly information, if this is not a mistake, is totally lost, right? So on the other hand, this is more representative now of an average day. But what I want to show you is, because people say, oh, don't use the mean, use the cool median. Yes, okay. However, the median the advantage of the median can also be a disadvantage because you suddenly lose this. However, if you calculate this with 38, this number would be way higher and would misrepresent it. You see, it's not always, everything is not always good. There is not always a winner here. Like, this is what I want you to like critically think. Look at this information. So what we could, for example, do, we could also put out the max value. On top of it, we could also put out the mean and the median, right? And then we would see the difference. And then actually the median difference indicates what a lot of you said, skewed data, right? And so we would see that, okay, there is some sort, if this is like, we can calculate this and we would see, okay, there is some sort of mean that potentially harms this, okay? So here, let's see. So I actually have an example like this here. So as I said, order data, for example, here we have, this is the same example. So the median is 3. So the median is calculated by just order them and pick the middle value. If it's like 2 middle values, you can usually divide it by 2. So here I have this example with 21. You can see this is 3.5 and the mean is 7.2. So you see this difference here. This indicates skewed data, right? This indicates skewed data. So data that is not like symmetrical, okay? So what I'm trying to say is that if I have both numbers, I see that there's something wrong. And then if I have the max value on top of it, I can see, oh, okay, max value and then also standard deviation. Then I get everything. So having said that, we're gonna move, okay, there is a central tendency. This is the mode. The mode can only be done by nominal. So basically, let me see. This can be done by numerical, of course, can everything, and ordinal, right? This can be done only by numerical scale. So numerical, I mean ratio and interval scale when I talk about numerical scale. And here, this I can only do, so the only I can apply it is nominal scale, right? So central tendency, the mode, I can do nominal. I can also do it for numerical and ordinal, right? So because I can always say what's the most frequent, but this is the only thing I can do in nominal. So this I cannot do for nominal, right? So this is numerical, not nominal. And here I can do numerical, numerical ordinal, and nominal, numerical ordinal, okay? So this is the only thing I can basically do for nominal data types. I can just say, okay, this is the most frequent. This is basically the most frequent thing, okay? All right, so yeah, you can see it here. Just pick out the value that's most frequent. I mean, don't have to go into details here. If for example, here we have 2 times 8. Like if there are multiple values that are frequent, then it contains multiple values. Okay, it's the only really difficult thing here. Okay, but now I said here in our example, we actually saw that we need that is some kind of important to see how data spreads, right? Why is it important? Well, and I want to tell you this from the view of predictive modeling. Okay, now, and for this to understand, right, because I don't need to teach you the formula for variances. You know this. This is not what we are here for. We're here for predictive modeling. Now, I'm going to show you something, right? And this is like a basic, maybe even philosophical concept. Okay, so we have these variables. We have this data. So we have this variable y. This is what we want to predict. This is our target, right? Target. And then we have, I'm going to call them feature one and feature two. I'm going to make it really easy. Okay, feature one and feature two. And these help us. These are our features, right? And these help us to predict y. So this is what we want to do. So we want to build a model that contains f1 and f2, and they predict y. Okay, easy. Now, the important thing is, and this is like when we talk about machine learning, this is where we have to be concerned about the parking lot. Remember the analogy? We take a child and drag it through the parking lot and say, this is a sports car, this is not a sports car. So this is our training data, right? Training data. So sports car, look at the car, look at this feature of the car, look at this feature of the car, look at the rims, look at the color. This is not a sports car. Rims, color, this is not a sports car, and so on, right? So the idea here is, and that in order to train the model, right, our parking space, our parking lot needs to be really good. And by good, I mean we need to basically cover a lot of cases, because what happens is we train the model and then future cases will come in that we've never seen before. So basically we need to cover a variety of cases that can happen. So here we have to cover a lot of combinations of the two variables, right? So 12, 1, 2, 3. So we want to, if this is a nominal variable, if this is a nominal variable, an ordinal variable, that we need to make sure that the data has a lot of combinations, right? So that the data has some sort of variability. So whenever this data changes and this data changes and then they change together, this will influence y. Assuming that they have an influence on y, we assume that for now, okay? If not, then it doesn't matter anyway. We just throw them out. And this is important that we have some variability in the parking lot, right? So we need to have some different kind of cars, and so that the child can learn, right? How different sports cars look like. Like there's not only one type of sports cars, and the child also needs to learn what normal cars look like, right? So we need to have all sorts of cars here, right? So it's very important we get some variability, and the variability is actually done by here the combination of these two. So this car is defined by the combination of these two. This car is defined by the combination of these two, and so on. So, and knowing like how this combination actually varies, right, will give us an idea, right? Will give us an idea. And so, however, this can be good or bad. If I have a lot of outliers, then I have to ask myself. So I have not a lot, but usually I don't have a lot of outliers, but then they wouldn't be outliers, but they could be really into different directions. So it could be either small value or large value here. So this would mean that usually the average difference between the values would grow. So, and this is what we achieve with looking at the variance. Now, the variance is actually a very complicated concept to understand. It sounds easy, but it's actually a very complicated concept to understand. So we're going to do this using the example here. I'm going to reflect it onto the part. Now, ER arrivals in 1 hour. Again, similar example. So we have this right here. And the variance is the variance really 6.8? I don't think so. Is the variance 6.8? Okay, let's see. Okay, so what we calculated is we take the value. So what we're going to do is we're going to look at the formula and we're going to act as if we were to invent it, right? So this helps us. So we're going to ignore this for now. So what we're going to do is we're going to calculate the variance. So at the variance, how does it work? We have this thing here. And so we have the mean here, right? So we have the mean. So this can only be done, of course, for numerical data, right? So we have the mean. So this gives us an idea of the central location of the data. So, and then we have our data points, right? So, and now we know that there are some data points that might be far away from the mean, right? So like this. Then there are data points that are close. Now I'm going to show you something, right? I'm going to show you something. So this is the mean. I'm going to show you a different example. So this is example 1. I'm going to show you a different example, right? So again, I have the mean. It's somewhat in the middle. And let's say the mean is 10. And here the mean is also 10, right? But you see that here the data spreads, but it spreads evenly around so that the mean comes to 10 and here the mean also comes to 10. But the spread, how they spread around is quite different. So here, in this case, right, the problem is my parking lot, right, so that I train my model is pretty limited. So I have pretty limited variation. So this could have two reasons. Either this is just the way it is, so this variable just moves in this realm. So there are basically, this is just the normal and this is fine. So it doesn't have to be bad necessarily. However, it could be that the data set I have misses a lot of data variations that might help me, right? So, and this would be a problem. So what if these are actually cool data points that I need here, right? So these are things that lead to different situation regarding to y, and I don't have them. So my prediction model, when a new thing comes in, will have problems predicting it when my values lie here, right? So if everything is okay, if this is a normal, it's okay, right? I'm just saying you cannot really like infer that. However, it's very important that you know that this can be, that you can compare variances and then you get an idea on what's going on. And now if we look at the formula, so basically what we do is we add up all these differences between the mean, between the mean and the value, right? So what here in parentheses is one of these things. This is one difference. So this is difference number 1. So this is for n equals 1, not n equals 1, but for the first thing, for I equals 1, this is I equals 1. This is I equals 2, right? And then we don't add the values, we add the differences. So basically, what this is this is a mean of differences. Like if this here with the square is like, if I call this set, then what I do have is I just have, we can also ignore that one, that doesn't matter. This is just a statistical thing, so it's not biased. We don't really care about this in machine learning. So this is basically 1n of zi, right? So this is basically the mean of squared differences. Now, quick question. Why do I square the differences? Why do I square a difference? Why do I square the differences? Why can't I just add up the differences? Why do I need to square? I mean, this is a difference, this is a difference. I can just add them up, right? Why do I need to square them? I mean, you see the square here. We don't ignore that, right? But why is it there? Because there would be negative values to avoid negativity. Why? Non-negative rule for variance? There's no non-negative rule for variance. I mean, yeah, but why? I mean, yeah, you know that there is the rule, but why is it there? I mean, the question is the practical. Why did people invent it that way? We are inventing it now. There is no negativity rule now. Why? Easy to understand the dispersion of the data. Not really. I mean, everybody understands negative because negative plus positive. Yeah, that's the correct thing. Because negative, positive The problem is, what you see here, I had the right-hand side. So you can see this formula. So this minus, if I take this one and I subtract the mean, so everything here will be positive on the right-hand side because these values are larger than the mean, but everything here will be negative, right? So these values will all be negative. So these differences, when I don't square them, these differences, they are all negative, right? So, and now if I don't do this, we had like, for example, here we have -1, -2, -10, right? And then +2 and +10. So you can see they equal each other out, and I end up with -1, right? So, and the difference is -1. So first of all, yeah, it's negative, but I could use it. But the question is about the difference, right? So the average distance would be -1. It's not true because the distance here is 10 to 1, the distance. So if I need to square this so it doesn't equal each other up, right? And also a nice effect, by the way, is a nicer effect, by the way, is that larger distances, they also appear bigger, right? So obviously, if I square 10, it's not linear, but it's a square, right? So it goes way up here. So, and this is why we need to square. So basically, this is like the average, and this is the average of distances, right? So this is what you can explain. The problem here is that this is rivals squared. So if you want to, this is not, this is even confusing when you don't have like a metric like meters or centimeters or Celsius. But here this is a rival squared. So I cannot really interpret this. So this is why we just take the square root and then we call it the standard deviation. This is what you see. And this is in the original unit. So we see that on average, and this is really important because people usually confuse this with like some sort of range, and it is some sort of like plus minus range, okay? But it's not like max and min. Like min and max are really values that are the borders of your data, right? And the standard deviation can be somewhat in between. Like this is minus 2.6, this is plus 2.6, and here is the mean somewhere, right? So this is the standard deviation. This is the average deviation that we have. And there can be, of course, like is data with outside of this and inside of this usually, right? So doesn't really matter. But just to make sure that you don't think this is like the corridor of min and max, like min and max. And usually I love min and max values. So people usually forget to give them. And I will never understand why. Okay. So when we look back now at this thing right here, so this is our data, right? And here you see the standard deviation here. These are actually true values, by the way. So standard deviation, this is the average. Like you can see, this is the average deviation, right? So the average deviation from a data point to the mean. And again, this of course is also this is not robust to outliers, obviously, right? So if you have an outlier, our spread can go way up, right? This is also very important, but we already discussed this. So also outliers will even more so because it's squared now. So it's even worse, right? It's even worse than with the mean. And yeah. So, and again, what does that matter for us? Because we need to take care of the parking lot, of the training data. We need to have a look that we cover a lot of variability. So if you want to memorize this, think of the parking lot, right? So each car is represented by the combination of features that we have. And if we only have yellow sports cars, like the model will think that yellow is a very important feature because we don't have other combinations. So the variability of this feature will be very low. So it will indicate here, right? So this is like something that helps us to understand, but also it helps us to see how the data is really distributed. And we will see this when we talk about box plots. But the distribution of the data is given usually or can be expressed by the spread and by the central tendency, like here. So we get an idea of it. And we also get an idea on what a lot of you said already, anomalies, right? So if we have a box plot, which we will see later, you have outliers, you can see this. You can also see the distribution now in the box plot. So is the distribution skewed, for example, right? So we will have this. So this is pretty cool. We will skip this, right? You can say we skip this. It's really more statistics, so we skip this. So please remember, this is like, right? Don't have, you can look at this, but the quartiles, the quartiles are really something that we don't, I will explain them anyway when we talk about the quartiles, right? When we talk about the box plot, I will quickly explain this, but don't really. Okay, so univariate graphics. So this is the box plot. Here I can actually explain it, right? So this we will not skip. Now, if you look at the data, the box plot is a very cool way, and this is the last thing we will do today. So the box plot, and now we are here in graphics. Now we are still in univariate, but we moved to graphics now. Okay, the box plot is one of my favorite plots. So, and it looks very complicated, but it's actually not. So the box plot is a box. Well, it says box plot, and the box is this here, right? So this is the box. You can see this is the box of the box plot. So, and the box has a left-hand side, right? Or sometimes the box plot is printed like that, right? So it would be then the lower end of the box. So here, what we see, this one right here, so if you turn it around, this would be the lower end, is what's called the first quartile. And this just means that 25% of the data is smaller than this point and 75% is larger than this point. That's basically it, right? So this is like 25% of the data covered here. Then the top thing is 75% of the data. So this is the third quartile. And in the middle somewhere, not in the middle, can be somewhere here, is the median, right? And the median is obviously the 50%, because remember what we did when we said the median, we ordered the data and we looked at the middle. So 50% of the data is to the left side of this point and 50% of the data is to the right side of this point, approximately, right? So, and here it's the same thing. So if I order the data, I look at the point where 25% of the data is to the left and to the right, and this is the point that I note here on my scale. So usually, of course, there is a scale here, right? So for example, age, this would be the age. And then I have a point like here, this would be age 20, this could be age 60, and the median would be age 51, something like this, okay? So usually I have a scale for this, obviously. And yeah, that's basically it. And so this is the box of the box plot, right? And now the length of the box, right? This is what we call, obviously, the interquartile range. So this is the difference between the first and the third quartile. Very cool word. So if I can say, hey, did you look at the interquartile range? It's a very cool word. And it's just the difference between the first and the third quartile. It's basically it, right? And it has other meanings because you can see this is the box of the box plot, but the box plot always have what we call whiskers, antennas, whiskers, whatever you want to call them. Usually they are called whiskers. So these are these things right here, right? And the length right here, usually, right, the length right here, usually is calculated by 1.5 times the interquartile range, right? So this is usually, the important thing is that optically, it doesn't look that way. So this whisker doesn't, of course, here is not 1.5 times as long because it's the visualization. You just have to know this. And everything that lies beyond that is where outliers can be visualized, right? So this is usually how a box plot works. And so, and what you can, this gives you a nice idea of the data. So for example, here we would have the box plot right here. So we construct the box plot for this type of data. If you want to do it, you can do it. Like we have here, we have these values, quartile 1, quartile 3. And so this is like Q3, this is 9, this is 5.5, this is 8, and the median is 8. And then you can see this is the box plot. This is 1.5 interquartile range. And yeah, so yeah, sorry. So we have a question. Let's see. Are the assumptions same for candlestick chart assumptions such as quartile and whiskers? I have no you mean the candlestick charts in the stock market analytics, right? The candlestick charts. I have no idea. I'm sorry. I think 10 really sorry. I'm not into financial stock market shenanigans. I know that people read the candlestick charts. I assume that the candlesticks are somewhat differently defined though, right? So, but I cannot say for sure. I can look it up, but so can you. I think if you Google now what a candlestick chart is and how is it comprised, you're faster than me. But I will look it up after the lecture. But this is a more financial topic, and maybe it's a good question for Professor Lucas. He might know it, right? But I think, but I'm not sure. The answer is I'm not sure. I have seen them. I know what they do, but I cannot tell you exactly how they are constructed, right? So let's say Tristan Googled it. Let's explore. Let's explore because we're done for today. So I'm actually done for today. So let's read the answer of Tristan that Googled it for us. Candlestick charts depict the open, closing, high and low. Ah, yeah. So exactly. Yeah. I should have known this. Yeah, this is a little embarrassing. I actually knew this, but I was confusing it with another kind of chart. So probably it's like depict the open, closing, high and low prices. So you have the high price, right? You have the high price, the low price, and the opening price, right? Low price, closing, direct to open, closing, high and low, four. Okay, I'm not sure. But yeah, four prices, okay, candlestick charts. So we have these things. The shape can shrink or enlarge depending on the relation between these prices. The color and the wider part of the candlestick indicate where the stock closed high. Ah, yeah. So you have like basically this, like you have these four things, right? I think like, so it can be like this, it can be like this, right? Yeah. Probably you have the four sides. Cool. Thank you, Tristan, for enlightening us what a candlestick chart is. Yeah, cool. So it's not like uh, it has some similarity, but it has nothing to do with the quartiles. It's just depicting four values and just putting it into one graphic. Okay, so with that, thank you so much for joining. The next week we will continue. Obviously, we'll continue with this whole thing. Then we will do bivariate analysis, and then we will go straight into data preparation, right? Which is more a little bit more exciting. But you can see we have some problems here, some data problems, right? So next time we will detect some cool data problems and discuss what it means for us and for prediction when these problems occur. So thank you so much for joining. See you next week. Bye bye, everyone. Have a lovely week. Bye.